So this is a really fun section that's not really about algebra, but more so about just numbers in general. And it's a really cool study that if you feel like you're not very good at algebra, you can feel encouraged from this because it's not very algebra-y, if that makes sense. But sequences and series is going to be what this next chapter is all about, and it's pretty fun. It's just something different, and sequences is only going to be an ordered list of numbers. Okay, so as long as the numbers are in order, you're good to go. Sometimes they'll give you numbers out of order and they expect you to put it in order, so it's not super difficult. Everybody should be able to do that no problem, go from least to biggest. So this can be limited or unlimited, and you will automatically know if a sequence is limited or unlimited because of a certain thing. And if it is limited, you'll know it ends with a number. In this particular case, they're saying that this could be any number, so that's why they put n, which is a variable. But if it's unlimited, then you will end with a ... We call this an ellipse, or in English. So there's some things you need to know about this. The domain is basically what you're plugging in. That's the same thing as algebra. You should always, or typically you should start with 1, so you're plugging in the first number, the second number, third number, etc., until you get to your last number, which it could be anything, so that's why they use the term n, okay? And you could think about this as like the first number, and the second number, and the third number, and therefore the nth number. And so obviously whatever you plug in, it's sort of like a function. What you plug in, you get something out. It could be the same number, it could be a completely different number, and so because of that, we would say that our range is a sub 1. A sub 1 is just a way to say that you're plugging in the first number, so you can see it's sort of represented in the annotation itself. You're plugging in the first number, and because you're plugging in that first number, you end up with a different number. And instead of confusing you by adding like all these different variables, they just keep A so that you know that it's the range. All right, but this time we get a different number because we plugged in 2. This one is we get the third number or we get out a third range because we plugged in 3. And so you can do all the way until the very end where you plug in the n, and so your last term would be when you plug in the last number, which in this case we don't know what it is, which is why it's called n. Okay, so this is just the annotation that they use for these types of series and sequences. And so just to show you another example, we with different numbers, right here we have this example. We have a finite sequence. Notice how it ends with a number. Okay, so we know because it ends with a number, it's going to be a finite. There's a limited number. It has an ending, a significant ending. But the next one ends with an ellipses, or ellipse. I guess I should look that one up. All right, so these are called ellipses, like I thought. And so a sequence can be specified by an equation or a rule. I should probably retype that out. A sequence can be specified by an equation or a rule. For example, in our example over here, this can be described as 2 times n. And so there's 2 different ways that you can write this. You can write this as a series or sequence sort of rule, which is a sub n, that's following the same annotation. Or if you want to write it like a function, which is very algebra based, then you could do the function of n equals 2n, okay? A sequence can start at 0 or 1, okay? And typically, if it's not specified, then it's automatically going to start at 1, okay? And that's something you really, really, really should know, all right? If you don't know where it starts, just assume it's a 1. Starts at 1. So let's go ahead and do the first example. The example 1 just says write the first 6 terms of the sequence. Now we can do this in a number of different ways. I typically just like to use my calculator, but just so you understand what the process is behind all of this, you can set up a table for that first example. Let's say we have to plug in the first 6 numbers, so this would be our sort of our domain, or what we're plugging in, which is n, okay, and then what we're getting out of it, which is the f of n. All right, that's after we plug it in, and it says to plug in the first 6 terms. First 6 terms is just 1 through 6. So 1, 2, 3, 4, 5, and then 6. Again, after we do this first one, we can just use our calculator. It's not going to be super difficult. But we're plugging it into the rule. They gave us the rule, which is right here. So I'm going to say that this is 2 times 1 plus 5. That means the next time I would plug in a 2, and then I would plug in a 3, and then I'd plug in a 4, followed by a 5, and then finally 6. And I can use my calculator to solve all of these out. So that first one would be 2 times 1 plus 5, which is 7. 2 times 2 is 4, plus 5, which is 9. 2 times 3 is 6, plus 5 is 11. 2 times 4 is 8, plus 5, which is 13. 2 times 5 plus 5 is going to be 15. And then 2 times 6 is 12. Plus 5 is 17. And so my answer for this is going to be the list of these numbers right here, all of these. So I would say, and I can write it as a sequence. I could say it's 7, 9, 11, and I'm writing small because I sort of don't have room here, 13, 15, and 17. And because they asked for the first 6 terms, I'm going to end it with that. I'm not going to put my ellipses. I'm just going to end it right there. So the same sort of process happens again and again. And so I can use my calculator for the next portion, or I can just do it in my head. So an example 1.2a, it just says plug in the first 6 terms and square it. So if I plug in the first one, 1 squared is going to give me 1. 2 squared is going to give me 4. 3 squared is going to give me 9. 4 squared is going to give me 16. 5 squared is going to give me 25. And then 6 squared is going to give me 36. And so this is my answer. Again, we're using our curly brackets so that we know that this is a sequence, just like we see at the top of our notes here. All right, so the rest of these are the same idea. And I'm going to use my calculator for the next problem. So here I have my calculator. I went ahead and plugged in example 1.1b, which says a sub n equals -3 to the power of n minus 1. And since I'm plugging in the first 6 numbers again, the first 6 terms are 1 through 6. So instead of plugging in like an x right here, I plugged in the number 1 since I have to plug that in eventually. Because I'm using this calculator, I can just press enter. I do want to point out that I definitely have to use parentheses here. If you don't use parentheses around that -3, you're going to end up with the wrong answer. So we press enter and we get the answer of 1. All right, so if I do the same thing again, and I'm going to do a shortcut, instead of rewriting everything, I'm just going to press second and then entry. As you can see right here, it says entry, and it just pops back up. And I'm just going to modify what it is. So I'm going to go over to where that n was and plug in a 2 now. Enter. Okay, the next one would be -3. Okay, and I just keep doing this until I get all of my terms. Okay, so I have the first 3, so I'm just gonna write that down really fast so that way I can write all my answers down at the very end. All right, so now that I've written all those down, I can keep going. Second entry, bring this back over. I need to do the 4th term. Do it again for the last 2 terms. 5. And then finally my last term, 6. All right, so I have all my numbers and now I can just copy them over onto my paper. So from my calculator, I got my sequence of 1, -3, +9, -27, 81, and -243. And these are my answers. And I can keep doing the same thing. And I know some of you guys probably might not have the graphing calculator with you at home, so I did want to show you what it would look like if you were to use just a calculator on your computer or maybe on your phone. So most computers have this standard calculator just programmed into your computer already. And so you can actually change it from standard to scientific by clicking on this menu bar over here. So if you click it and go down to scientific, it now changes it to this sort of screen. And just to get used to it, I have some computers are a little bit different. You can do something that you know for sure. You can try 5 squared. We all know that equals 25. Sometimes calculators require you to like plug in things backwards, so we just want to make sure that's not the case with this one. So I'm going to press 5, and then there's this button over here which is x to the y power. This is just saying that you're going to plug in both the base and the exponent. So I'm going to click that, and if you can see up here in the top of your top right hand side, you have sort of like a caret, sort of how our calculator does it. And so I know that this is going to be what I need in the correct order. 5 squared is 25. Okay, so now I'm going to work on example 1.2b, which says 4 to the power of n minus 1. And thankfully I don't have parentheses. That makes my life a whole lot easier. So I'm going to go ahead and work out all of these. And I'm actually going to do it in my head, part of it in my head, my exponent portion at least. So if I were to plug in a 1 into that n, 1 minus 1 is 0. So it's going to be 4 to the 0 power, which equals 1. Okay, then I do the same thing again. 4 to the power of, now I plug in 2. 2 minus 1 is to the first power, which equals 4. And I just keep doing that. And if you think about it, it's just adding 1 sequentially. So I'm going to do 4 to the power of 2 now, 4 to the power of 3, 4 to the power of 4, and then the last one, 6 minus 1, is going to give me 5, so 4 to the power of 5. And now that I have all of these numbers, I can write them in my answer area on my screen here, on my notes here. So this was 1, 4, 16, 64, 256, and then finally 1024. And these were the first 6 terms for this. All right, so sometimes though your calculator is just going to be more difficult than anything. And so for this next one, I'm going to go ahead, example 1.1c, I'm going to go ahead and just do this one sort of in my head again. I see that I'm plugging in n on the numerator and the denominator. So I'm going to plug that in. That'll be 1 at the top, and 1 plus 1 is 2. Okay, that means the next one would be 2 up top, and then 2 plus 1 is 3. So I can sort of see a pattern emerging here. I see that everything is increasing on the numerator and the denominator. There's just one number difference, like there's 1 and then 2, 2 and then 3. So if I just follow that pattern, I'm going to get 3 and 4, 4 and 5, 5 and 6, and then 6 and 7. And so that is my first 6 terms to this particular sequence. All right, the next one is the same idea. You have to end up doing it in your head, but with this one, your fractions might actually reduce a little bit. So I'm going to go ahead and do some of it, just plug it in, and then once I'm done plugging it, I'm going to see what I can possibly reduce. So if I plug in 1, 2 times 1 is 2, and then in the denominator, 1 plus 1 is 2 again. So I can actually reduce that, but I'll do it at the end. Plug in 2. 2 times 2 is 4. And really, sometimes just to make my life easier, because flipping back and forth is really hard for me sometimes, I will just do all the numerators. So 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. And then 2 times 6 is 12. Okay, so that's 1, 2, 3, 4, 5, 6. Yep, that's the first 6 terms. And now I'm going to go ahead and do the denominator. I plugged in 1 for the first one. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. And then 6, and then 7. All right, so now that I'm done with that, just plugging in, I can just double check to make sure I, have everything in lowest terms. 2 over 2 is 1, so I can reduce that. 4/3 is already in lowest terms, so I'm going to just keep that. 6 over 4, well, 6 and 4 are both divisible by 2, so that'll give me 3 over 2. 8 over 5, can't reduce that, so I'm going to bring that one down. 10 over 6, I can reduce that. 5 over 3. And then 12 over 7, I can't reduce, so I'm just going to carry that down. And so this is going to be my answer. So that's all we're doing for this first example. We're just finding the first 6 terms. So example 2 is a little bit more difficult. This one is just, can you figure out the pattern? And once you figure out the pattern, you can find the next term by plugging in sort of the next thing. with this, we have no specifications if we're starting at a 0 or a 1. So therefore, you must always assume that we are starting at 1. Okay? And so typically what I like to do is I like to look at the first two terms and just sort of ask myself, you know, what do I have to do to get to the first term, and then what do I have to do to get to the second term, and then how do those two relate? So for example, if I look at example 2.1a, I see that I have like -1, and then -8, and then -27, and I'm going to ignore the negatives for a second. I have 1 and then 8, and I can get 1 many different ways. I can do 1 squared, I can do anything to the power of 0, I can do 1 cubed. There's a lot of different things. So the first term doesn't actually tell me anything, but the second term does. I can't square a number and get to 8, but I can do 2 cubed. All right, so I can think about that. And then if I go to the next one and I ask myself, well, can the next one be plugged in with like 3 cubed? Well, it can. So I can sort of see the pattern happening here, and then I just notice that all of these numbers are negative. So I figured out the rule pretty easily with that one. So my rule, and I would write it like this, a sub n equals negative, and the number I plugged in is going to be my variable, n. Okay, the cube didn't change at all, so that carries over. And if I were to find the next term, that would be if I plugged in a 5, okay, that would be -5 cubed, which is going to be -125. So my rule is here, and then my next term is here. And that's sort of the pattern we're having for all of these. So go ahead and just look at the example 2.2a really fast. Just look at it and try to figure out, can you see the pattern? So in example 2.2a, we do have a pattern. If you look at it pretty closely, you can see that it's so close, very, very, very close to perfect squares. Like this could almost be 1 squared. This could almost be 2 squared. And this could be almost be 3 squared. And this could almost be 4 squared. The only thing with all of this is that all of them have been increased by 1. And so that is actually our pattern. It's the number squared, and then you add 1. And so our rule for this would be a sub n equals, okay, the base was changing every time, so it would be n squared plus 1. So if I wanted to find the next term, which seems to be, again, the 5th term, it'd be a 5, or a sub 5, 5 squared plus 1. Well, 5 squared is 25. 25 plus 1 is 26. So my rule is n squared plus 1. My next term would be 26. All right, same idea with the next one. You have to ask yourself, what are you going to do? For example, 2.1b, what do you have to do to get to that first term? So sometimes if it's not as obvious as like cubing or squaring, you can sort of write a list to see what works. So for example, I would write a list to ask myself, how did I get to 3? Is it n plus 2, like 1 plus 2? Is it 3 times n? Is it something different? So I can use these two to sort of see where I'm going, and if neither of them work, I have to try something a little bit different. So this works for the first term. Let's see if it works for the second term. 2 plus 2 is 4. Well, then that means this one's out because this one has to be 2. Something happens to 2. 2 times 3 is 6. Okay, so that doesn't work either. So now I have to do something a little bit different. Maybe I have to multiply by 2 because I see all of them are odd. And then maybe I can add by 1. So if I multiply by 2 and then add by 1, that automatically gives me an odd number. So I can check that. 2 times 1 is 2, plus 1 is 3. Okay, so that works for the second one. Let's erase this really fast. All right, if I plug in 2 times 2 is 4, plus 1, that gives me 5. Okay, so it seems to be working. 2 times 3 is 6, plus 1 is 7. Okay, so I seem to have found it. This is going to be my rule. That's a terrible A. A sub n equals 2 times n plus 1. And really, these just take lots and lots of practice. Sometimes it's really easy to see, sometimes it's not easy to see. But the more you practice this, the better you get at it. All right, so then to find the next one, so I have 1, 2, 3, 4. Again, the fifth term, a sub 5 equals 2 times 5 plus 1. That will give me 11. So my next term for this one is 11. All right, example 2.2b. This one, I see something happening between the first term and the second term. It goes from a positive to a negative. And just from my experience as like a student in math and a math teacher, I know that when this happens, we know that we have our number being not really squared, but we have a negative number as the base, okay? Typically, that negative number is squared, and that's what happens, or I guess not squared, but has an exponent of some sort, and it just rotates between positive and negative. And so from here, I can try a couple things. I can try a base of 2, or I can try like a base of 3. That's typically what it is. It's not usually a base of 1 unless it goes from like 1 to negative 1 to 1 to negative 1. That's when we would have like a base of 1. But I'm going to try 2 and 3 and see if that works. And then I obviously need to have an exponent, or not an exponent, a variable. And so I'm going to try to put that as the exponent, n and n. All right, so if I plug in a 1 for my first term, negative 2 to the first power, that's going to give me negative 2, so that doesn't quite work. So I'm going to try to change that formula a little bit so it does give me 1. I can add 1, but that'll give me negative 2 squared. So instead of doing that, I'm going to subtract 1, see if that gives me what I need. So if I were to plug in, and I'll write it down here so you can sort of see my thought process, negative 2, 1 minus 1, that gives me negative 2 to the 0 power. Anything to the 0 power equals 1. Okay, so that's the first one. Then I'm going to try the second one. 2 minus 1, that gives me negative 2 to the first power, which equals negative 2. All right, so that works out. This is looking pretty good. First try, good for me. Negative 2, plug in the 3, negative 1. This will give me negative 2 squared, which is 4. All right, so I seem to have it. This is great. I write my rule, a sub n equals negative 2 to the power of n minus 1. All right, and to find the next one, I would plug in a 5. Negative 2, 5 minus 1, which will give me a negative 2 to the 4th power. So that's going to give me a 16. All right. Again, some of these are going to be really hard. I try not to give you too many that are difficult, but I do want you guys to sort of get used to it and just sort of look at these so that you can get comfortable with them. All right, so let's go to the next page of your notes. So this next part is, now that we're taking our sequences, which is just an ordered pair of numbers, we're going to take those numbers and we're going to add them up. That's all that this next section is. So a series is when the terms of a sequence are added together. So that is really important to know, and it's sort of already highlighted for you, but I'm going to go ahead and do it anyway. Again, it can be finite or infinite, and so you can see sort of the difference. We have our finite series where it ends with a number, and then we have an infinite where, oh look, there's the ellipses again, so we know that we have that. You can write it in summation notation, which is just when you write everything out like this, or you can write it in sigma notation, which is when it has the sigma, the Greek letter sigma. If it's infinite, in the sigma, you're going to have the infinity symbol. So I just wanted to point that out to you really fast. And just maybe off to the side, write, your upper limit, which I'll explain in a second. But I'll say n equals infinity with an infinite series. Okay, remember, an infinite series is gonna have that ellipses. Okay, so having this sort of off to the side will help you as we go to the next part. So there's other things that you should probably know, and we'll dive into this a little bit more later. So just sort of have this in your mind off to the side. I'm not going to go into it too much right now because it is going to be 8-2 and 8-3 for you guys. But I am going to talk about sigma notation so that you understand what the hickety hey that's all about. you have your sigma. The sigma, again, just represents you adding up all the numbers in your sequence. So you have what you call a lower limit, which is where you start. And typically that's going to be represented by I equals 1, because remember, unless they specify, you start at 1. The upper limit is going to be where you stop. So if it's a finite, oops, that's not a very good one. If it's a finite sequence, then it's going to be a number, n. But if it's an infinite series, then it's going to be an infinity symbol, which is what we wrote up here. Okay? The argument is just the rule. So the rule that we practiced in example 2, that's what we're going to write here. And that's usually represented by x sub I. And that's just telling us that we're whatever. There is something I need you guys to know, and that is when you're doing this number down here and here match. So when you're writing your rule, we're going to plug in an I. It does change. Sometimes it changes to a K. Sometimes it changes to an X. Sometimes it changes to an N. It just changes. But just so that you know, whatever you have in the lower limit, whatever variable you have there, it also needs to match in the rule. Okay, so your lower limit and your rule have to match, the variables at least. Okay, so now that we've talked about that, let's go ahead and go down to example 3 just to see what that's all about and practice writing our sequences, or in this case, our series in summation notation. All right, so here are our beautiful examples, or really it's already in summation notation for us. We need to write in sigma notation. So we can, again, remember that when we are starting this off, everything starts with a 1. So if we look at example 3.1a, we know that we had to plug in a 1 to get this 25. So the easiest thing to change it from a 1 to 25 is to multiply it. So that means when I plug in a 2, it's still multiplying by 25. So 2 times 25 is 50. Okay, so that works out. 3 times 25 is 75. So we can see the rule pretty quickly here. The rule is 25 times what number we plug in, which I'm going to use an I in this case because of our notes right here. We used an I here, so we're just going to keep everything the same. The other thing I have to ask myself is, well, what number did I start with? Well, I started with 1 times 25. And then what did I end with? I ended with a 10 times 25. That's how I got the 250. So when I write it in sigma notation, okay, my lower limit is I equals 1, and my upper limit, where I stop, is at 10. And what's the rule? Well, the rule is, and I'm going to use parentheses, 25 times I. Again, you can change the variable, okay, but you just have to make sure they match. So if you wanted to, you could change it to a K, you could change it to a Z if you want. It doesn't really matter. Just make sure that those two variables are the same. All right, same idea with example 3.2a. Same process again. All right, we have to plug in a 1, so it seems to be 1 times 5. We can check with the next one. 2 times 5 is 10. Perfect. And so that means we're ending with a 20 times 5 to get 100. It's not a very good 20. All right, so this would be our sigma notation is going to be from, and let's change the variable. Let's do K this time. K equals 1, that's where I started off with. And then my upper limit was 20. I ended with the number 20. And the rule was, and I'm going to put this in parentheses so I don't mix these up, 5 times K. So let's make sure that our variables match, K and K. Yep, and so this is our answer. This is our sigma notation. All right, I go to the next piece. And really the purpose of doing the example 1.1 was so that we could sort of see some rules already. In example 3.1b, we've done this example before. It is example 1.1c. So that rule was already there for us, but we can look at it and we can sort of figure it out. We see everything is just straightforward at the top. So if I were to write my rule, it'd be n. And at the bottom, if I plug in 1, I have to get to 2 somehow, so I would add 1 to get that. All right, so that's our rule, and now I can write my sigma notation. So I'm going to do sigma. I started with the number 1, so I'll use K again. K equals 1. And then our upper limit, well, we have these ellipses, and when you have the ellipses, you go to infinity, which is not a very good infinity symbol, infinity. So then our rule is n over n plus 1. So this is our sigma notation. All right, I'll let you guys figure out example 3.2b. I can do example 3.1c and then 3.2c, just so that you can see examples of that. But this one right here is very similar to this one. So I'll let you guys figure that one out by yourself. But if you need to know the answers, it's going to be on the teacher notes on Plus Portals. All right, so same idea with the next one with letter C. I can see we have 6 and then 36. The only thing I can think of with that one is this is like 6 squared, which that means maybe the next one is 6 cubed, and I can use a calculator to double check it, and it is, so good for me. So I have that. So I figured out my rule. So I'd write my sigma notation. I started with, and I'm going to change the variable this time. I'm going to do n. N equals 1. And we have ellipses, so that means we're going to infinity. And then our rule was, it was 6 raised to the power. So I'm just going to raise it to the power of n and make sure that my variables match. And they do. So I'm good. You know what? I actually made a mistake in 3.1b here. I used k right here, but I didn't here because I copied it from the front page of our notes. So I'm actually going to fix that really fast. All right, that should not be an n, that should be a k. All right, now it all matches. And so the last one that we have here is example 3.2c, right here. And I know I have to plug in a 1, and the only thing I can think of is maybe like 1 times 5, or like 1 plus 4, or maybe like 1 squared plus 4, or something like that. I don't really know. And then to figure out the rule, I see if I plug in 2 times 5, that gives me 10, not 6, so it can't be this one. 2 plus 4 would give me 6. 3 plus 4 would give me 7, so it looks like it's going to be this one. So if I write my sigma notation, I started with 1, n equals 1. The rule was n plus 4, okay? And then to get to the 12, that would mean I would have to stop at 8. And so my sigma notation is from 1 to 8, and the rule is n plus 4. So it does take some getting used to, but it's not super difficult. It's just practice makes perfect. So let's look at that last example on your last page, which is now we're going to actually add everything up. So series is all about adding up all the numbers in your sequence. But right now we haven't done that yet. We've just practiced writing it. So now let's go ahead and actually add it. All right, so here is our last example. And if you look at the very top, there's actually some shortcuts, and I'm going to go over those shortcuts in a second. But first things first, we need to make sure we understand how to do this. So let me make this a little bit bigger for us. Okay, that's a little bit easier. Let me just scroll down a little bit. Okay, here we have find the sum. So all we're doing to do this is just plugging in what we have. So this is our rule again. So we're just going to plug in between 1 and 5, and we're going to plug it into this I. So it'd be 8 times 1, and then add that to 8 times 2, and then add that to, etc., all the way until we get to 5. So here we have to 5. So now we can just multiply and then add this. 8 times 1 is 8. 8 times 2 is 16. 8 times 3 is 24. 8 times 4 is 32. And then 8 times 5 is 40. Take a calculator and add all this up. If you do it correctly, you should get an answer of 120. Okay? The example below that is the same idea, but notice how instead of starting at 1 this time, we're actually starting at 4. And that's going to happen sometimes, so that's okay. It's not a huge deal. But it would be 3 plus 4 squared plus 3 plus, and sometimes it's a little easier to see the rule if you use parentheses around it, 3 plus 5 squared plus 3 plus 6 squared plus 3 plus 7 squared plus 3 3 plus 8 squared. Okay, so we've plugged everything in, and then we can use a calculator to find out what all this is. If we use a calculator, we should end up with this. All right, so all I did was I just carried down the 3's, and I went ahead and just did my exponents, because remember, we got to do PEMDAS here. So now that I've done that, I can either add up everything with my calculator, or I can just sort of separate things, and it doesn't really matter. If you plug into the calculator correctly, you should end up with an answer of 205. All right. So let's look at the shortcuts now. We have example 4.2a, and it just gives us our sigma notation, and then it just gives us a rule of 1, okay, which is meh. So if you look at the top of your page 3, the first formula says sum of n terms of 1, and it gives you your sigma notation between 1 and n, and where again, n is just a number, and then the rule is 1. And it says whatever your answer is, it's going to equal your top number, your top, your upper limit. Okay, so I could go ahead and write all this out, which is going to be 34 ones. If I plug in the first term, it's 1. Plug in the second term, it's 1. And then the third, and then the fourth, and then all the way to the 34th. I could do it that way, but that's a lot of work, and I could just use the shortcut. So the shortcut just says that whatever this number is up top, that's going to be your answer. So my answer is 34. I don't even have to do it, which is really nice. Same thing with the letter B right below. This is, again, your sigma notation between 1 to 6 with a rule of k, and they give you a formula for it. It's the second formula on your shortcuts at the top. And the formula says that you can do, and they changed the variable to k, so I'm going to change these variables to k. K times k plus 1 over 2. All right, so my k, again, is just going to be whatever number is up top here. So I'm going to carry this over. Really, I'm going to carry it over here and here. And so this is going to be 6 times 6 plus 1 over 2. If I multiply this, or add it really, 6 times 7 over 2, which is 42 over 2, which equals 21. Okay, if I wanted to, I could write this out, okay? Between 1 to 6, I just have to plug it into k. If I plug in 1 to k, I get 1. Plug in 2, I get 2, 3, 4, 5, 6. If I add all these up, it's going to equal 21, which is the same thing as that. So it doesn't really matter how you do it. If it's small and you feel uncomfortable using the formula, go ahead and just write it out. This is pretty short, so it wasn't too difficult. But if you have like a larger one, like let's say this one down here, which we're going to do next, well, then in that particular case, you want to make sure that you use the formula. It just gets a little bit bigger. Okay, so let's look at those bottom two ones really fast. All right, so letter C's on example 4.1 and 4.2. These two are the same sort of idea that we had with our previous ones, except you have to think about it in a different way, because notice how in the formula, the shortcuts that they gave you at the top, everything starts at 1, but this one does not start at 1. Neither does this one, okay? And because of that, we're going to have to take away part of our answer. So if I were to just like follow the formula like normal, all right? Formula like normal for this one is just whatever your answer is up here, that's your answer. So this would be 36. But remember, this represents from 1 to 36, okay? But I'm not doing 1 through 36. I'm actually doing 6 through 36. So I need to subtract away 1, 2, 3, 4, and 5. So I'm going to subtract away those 5, which would be minus 5, right? So really, the answer for this one is going to be 31, because I'm not finding the summation between 1 to 36. I'm finding the summation between 6 and 36. Again, if you're a little confused, you can go ahead and write it out. You have, starting off at 6, again, you have 1. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And then you can count up all these ones and you can see it's going to equal 31 because 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got 10 in each row. So this is 10, this is 10, this is 10, this is 1. 10 plus 10 plus 10 plus 1 is 31. Okay, same idea with the other C, but this one is the formula, again, it's n times n plus 1 over 2. So I'm going to go ahead and just plug it in as if I were doing 1 through 25. So I have 25 plus 20, or times 26 over 2. That's going to give me a 320, actually, I'll write it over here. 325. But again, that's from 1 to 25. So I need to figure out 1 through 9 and take that away because I have to start at 10 here. Okay, so I'm going to take away 1 through 9. So if I plug in the 9 instead, because 1 through 9, my upper limit is now 9. 9 plus 10 over 2. That's going to give me 90 over 2. Or 45. So I'm going to subtract these two numbers. 325, I'll write it down here. 325 minus 45 equals 280. And again, if you want to plug it in just to double check, we're doing 10, 11, 12, 13, 14, 15, Lord have mercy, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. You can take all of this, plug it into your calculator, and it's going to equal 280. So it's the same exact thing. All right, hope this was helpful. I'll be posting some other videos to help you with some other additional examples. Some of it might be the same, but these are the notes for, or the video notes for the notes on PLUS Portals, and I hope it helps you.